Okay, something we think we know. We think we know that the derivative of e to the x is e to the x. Well, it is, sort of. Okay, what it actually is e to the x times the natural log of e. But that doesn't bother us because the natural log of e is 1, right? So it actually is e to the x. It's just that this has a value of 1. So it's e to the x times 1. But that leads us to the idea of what is the derivative of a to the x. Well, it's actually a to the x times the natural log of a. Now the natural log of a is just a constant, right? Natural log of 3, natural log of 5, natural log of 4.7. You can just put those in your calculator. So this is a constant, natural log of a times a to the x. So the derivative of 10 to the x is just going to be 10 to the x times the natural log of 10. Again, that's a constant. All right, the proof of this comes from the chain rule, but we're not going to go through the proof of that today. We're just going to do some practice. All right. So what's the derivative of 17 to the x? If f of x is 17 raised to the x, what's f prime of x? Well, that's going to be 17 to the x times the natural log of 17 times that constant. All right. What about this one? What about 42 raised to the x squared minus 5x? So if that's y, what is dy dx? What is the derivative? Well, that's going to be 42 raised to that times the natural log of 42. All right, that's just some constant times the derivative of what's inside. Well, what's inside? X squared minus 5x. So the derivative of that is going to be 2x minus 5. Okay? All right, one more, I think. Yeah, cosine of 14 to the x. So this is when what's inside is the exponent. Well, what about when what's inside is an exponential function? It's the exact same thing we've been doing. What is the derivative of the cosine? Derivative of the cosine is negative sine of whatever that is, 14 to the x, times the derivative of what's inside. Well, what's the derivative of 14 raised to the x? It's 14 raised to the x times the natural log of 14. Now the natural log of 14, again, that's just a constant. That's just a constant. All right, so that's the derivative of exponentials when the base is not e to the x. All right. So what about the derivative of logs? Well, we're going to use the same idea. All right. We have thought that the derivative of the natural log of x was 1 over x. Well, it is sorta. It's actually 1 over x times 1 over the natural log of e, 1 divided by the natural log of e. Now, don't worry about this too much because this is pretty much straightforward from advanced math. What is, if you remember, how do you find the derivative of, how do you find the value of log base a of x? Well, with the new calculators, I know you can change it, but the old calculators, you had to change that to natural log of x over natural log of a, right? So we could just say that this is 1 over the natural log of a. Whoops, my pen doesn't want to write down there. 1 over the natural log of a times 1 over x. So this could be 1 over the natural log of a times 1 over x. So if we wanted to take the derivative of this, if I wanted to take the derivative of that, the derivative of that is just this constant times the derivative of 1 over x. So it, whoops, that's not right, hang on. Hard eraser, there we go. Yeah, that's, I took the derivative before I was supposed to. All right, this would be 1 over natural log of a times the natural log, pen back, get the pen back on, times the natural log of x. So the derivative, there it is, that's what I was looking for. So this is just a constant, right? So a constant times the function. The derivative is that constant times the derivative of the function. So that's going to be 1 over the natural log of a times the derivative of natural log of x, which was 1 over x. So if this is y, then this is y prime. So this one isn't actually that hard. It comes straight from advanced math, just breaking that into two separate functions. Let's practice a little bit. All right. Whoa, why do I have two of them open? Close that one. Not that one. That one. There we go. Okay. Come back up here. Y equals log base 42 of x plus log base 10 of x. All right, so what, I'm not going to get y prime yet. I'm going to change this. I'm going to show you how this changes. This becomes 1 over the natural log of 42 times the natural log of x plus 1 over the natural log of 10 times the natural log of x. That is y. I just rewrote those into another form. So now y prime is just 1 over, it's this constant, 1 over natural log of 42 times the derivative of the function, which is 1 over x, plus this constant, 1 over the natural log of 10 times the derivative of that function, which is 1 over x, 1 over 10 here. So if I factor out the 1 over x, would be 1 over the natural log of 42 plus 1 over the natural log of 10. This is just a value in your calculator. It's just some constant in your calculator. All right? What about this? What about log base 9 of, what do we got here? Log base 9 of x squared plus sine x. Well, that's, the derivative of that would be 1 over the natural log of 9 times this, which would be 1 over x squared minus or plus sine x times that derivative, so that would be times 2x plus cosine x. So it would be 2x plus cosine x divided by times 1 over natural log of 9 times 1 over x squared plus sine x. Well, now this asks me for what is the slope at 1. What is f prime of 1? I put it in. I just put it straight in my calculator. I take 1 divided by the natural log of 9 times 1 over 1 plus sine 1 times 2 plus the cosine of 1, and my calculator tells me 0.6278. 0.6278. Okay, all right, let's practice this. All right, so now we have the idea of we need to practice on the idea of the derivative of piece functions. All right, do you remember piece functions from advanced math? If we had this, it was the function was in two parts, right? We would say, well, when, let me find a blue here. When x is less than or equal to 0, when x is less than or equal to 0, what's the slope of this line? See, the rise is 1, the run is -1. So this would have a slope of -1 and an intercept of 2. So when x is less than or equal to 0, the value of that function is, what did I say it was, -x plus 2. -x plus 2. So -1, that's not right. Okay, so when x is less than or equal to 0, the function is -x plus 2. The value of that function is -x plus 2. All right, when x is greater than 0, all right, see this piece right here, when x is greater than 0, the value of the function is 3, y equals 3. So what we're going to do now is learn how to take the derivative of these piece functions, the derivative of these piece functions. All right, one of the applications for taking derivatives of piece functions is finding the derivative of the absolute value of a function. I want to emphasize here, your textbook doesn't emphasize it, but I want to start off emphasizing right here. This is not the same as f of the absolute value of x. We're going to do that later. This is the absolute value of the y, the absolute value of the whole function. Okay, so let's look at this one. Let's see. Okay, is this function, is y is equal to the absolute value of x plus 2. Is this function continuous for all real numbers? Yes, and no matter what value of x you put in there, it's going to be continuous. But we know, just because we've kind of just shortcut told us, that it's not differentiable when x is equal to negative 2. It's not differentiable at x equals negative 2 because of that corner. Okay, let's see why. Let's see why that corner doesn't allow us to be differentiable. Okay, so let's look at this function. When x is less than negative 2, give me an equation for that function. Well, the slope is 1, and the y-intercept I think is going to be negative 2. Okay, since this is y is equal to the absolute value of x plus 2, right? It's the absolute value of x shifted over to start at negative 2. When I'm less than negative 2, it's the opposite of that value. So when I'm less than negative 2, it's the opposite of x plus 2. And of course that becomes negative x minus 2. All right, so when I'm less than negative 2, it's the opposite of that function, which makes it negative x minus 2. All right. When I'm equal to negative 2, that function has a value of 0. And when I'm greater than negative 2, since my y was positive, nothing changes. The function is still x plus 2. Now look at this right here. What is the value of the slope when x is less than negative 2? The value of the slope is negative 1. What is the value of the slope when x is greater than negative 2? That's 1. Now what we've said, what we've learned so far, is that when we have these corners, the slope does not exist. What I want you to do is see why. Alright, so if I come over here to x equals negative 2, when I'm less than negative 2, the slope is negative 1. So this is my picture of f prime. When I'm greater than negative 2, the slope is 1. So what you see here is the function is continuous, right? I can draw this function without lifting my pen. I can draw that function without lifting my pen. That function is continuous, but it is not differentiable because the derivative is not continuous. See how the derivative jumps here? The derivative, I can't draw the derivative without lifting my pencil. I've got to lift my pencil at negative 2. I've got to lift my pencil to get from here to there. So the derivative is not continuous, therefore we say this function is not differentiable. This function is not differentiable. All right. Let's see. Another application. What's that? Another application. Okay. What is this? What shape does this have? The square root of x squared minus 4. Well, let's think about this. All right, so this is, if I square both sides, I'll get y squared equals x squared minus 4. So this becomes 4 equals, x squared minus y squared. It's not a circle, is it? Because that would be x squared plus y squared. So if you remember, we want this set equal to 1, so I'm going to divide everything by 4. So I get x squared over 4 minus y squared over 4. You should recognize that as a hyperbola, right? That's a hyperbola with vertexes. It's opening sideways because the x squared is positive, so I know it's opening sideways, left and right, and the vertex is at 2, 0, 2, 0, and negative 2, 0. The center of this hyperbola is 0, 0 because it's x minus 0 squared minus y minus 0 squared. So the center is 0, 0. The vertexes are at negative 2, 0 and 2, 0. And of course the slope of the asymptote is 2 over 2 or 1. So that both of the asymptotes have a slope of 1. All right, but this is only the positive of that square root. All right, so this is the whole thing, but when I squared it and I take the square root of this, I'm only looking for the positive. So the actual shape of this, let me erase all this. This is where it comes from. Okay, but the actual shape of this is only the upper portion. Jeez, this is worse than erasing the whiteboard. There we go. The actual shape of this is only the upper portion. So it looks like this. So here's negative 2 and negative 2, and so it looks like this. Right? It's not very good. My asymptotes should have a slope of 1 there, but that's okay. Alright, so that's what we're looking for. Now we're asked to find f prime of this thing. How do you find f prime of that? Okay, again, it's a piece function, right? So let's look at what our pieces are. Our pieces are when x is less than negative 2, when x equals negative 2, when x is between negative 2 and 2, when x equals 2, and when x, I guess I can just say, is greater than 2. Yeah, I get near the bottom and things don't like me. Okay, so these are my 5 pieces. All right, when x is less than negative 2, this is my function. Right, when x is less than negative 2, let me find my pages. Then it's my original function. Right, when x is less than negative 2, oops, f of x is the square root of x squared minus 4. When x equals negative 2, see this is sort of like a corner. The function equals 0. When x is between negative 2 and 2, the function does not exist. When x equals 2, the function has a value of 0. And when x is greater than 2, the function has the square root of x squared minus 4. All right, see this isn't an absolute value, but we treat it almost like it is. It's a piece function. We break it into its pieces. So what's the derivative? What's the derivative of something raised to the 1/2? It's 1/2 that something raised to the negative 1/2, square root of x squared minus 4, times derivative of what's inside, which is 2x. So my 2's are going to cancel, and I'm left with x over the square root of x squared minus 4. All right. What about here at this corner? What about here at this corner? What do we know about that? The slope doesn't exist, right? So at x equals negative 2, the slope does not exist. Between negative 2 and 2, the function doesn't exist. So if the function doesn't exist, then there's no slope. At 0, again, the slope does not exist. And when x is greater than 2, it's going to be the same thing as up there. I don't know where that negative sign came from. I think it was part of the erase. It's the exact same slope. It's x divided by the square root of x squared minus 4. All right, so we break that into the pieces. Notice the function exists at x equals 2 and x equals negative 2, but the derivative does not exist. The derivative does not exist there because we have these corners, because we have these sharp corners. All right. Okay, I'm going to stop this now because Google's not going to be happy with me if I go too long. I'll get together a part.